a talk last week at a conference in San Diego, so I just grabbed those slides and brought them, and I'll just sort of skip through some things. I do underwater acoustics and specifically numerical solutions for the wave equation in underwater. And we're solving a specific problem right now, which is that sound in the ocean likes to go to the lowest speed it can. And usually there's a place along the middle of the ocean that has the lowest sound speed, and the sound stays in that sound channel. But there have been some observations where acoustic signals have been much deeper than that sound channel. And so we're doing some simulations now that incorporate the ocean bottom, which has what are called elastic properties, because it's like a table or a floor. It can shake in both a shearing way, where things cut across each other, and a compressional way. And so this is sort of new stuff, and that's what we're doing. Is we have this elastic bottom. We need to put a source in there, like an earthquake kind of source numerically, and then let these codes propagate to see how much sound gets into the water column. So let me just get to some pictures that are relevant here. There we go. All right, so this is a picture. We have a acoustic source right here, sort of deep ocean. I don't know if you can see on there with sort of deep ocean, but that doesn't matter. And the red parts are loud acoustics, and the purple parts are not loud. And so what we do is we break up this ocean, this sort of very simple ocean, flat-bottomed ocean, into a grid. And if there's 2,500 meters worth of ocean here, we probably have a grid point every half meter or so. So you've got 5,000 grid points in that direction, and then I've got 10 kilometers here, and we probably have a grid point every 5 meters or so. So we're really having to solve every step along the way, at every range point, every 5 meters, solve this differential equation to get this kind of picture. And this one, where the where the ocean is flat, this is for a single frequency for 10 hertz. The lower the frequency, usually the easier the computation. But for this kind of thing, it would run on I have a Xeon workstation in my office, and it runs on that in about maybe 2 or 3 minutes. But on my laptop, it takes more like 10 or 12 minutes. Okay, so that gives you an idea of that. If we do, I'll show you that in a second, something else, which is sort of a downhill thing, everything gets a lot more complicated. Here's another picture. We have a source, and then red is loud, so you compute all the way out along those grid points. But this range-dependent example on the laptop takes more like 25 minutes, half an hour, and on my desktop it's maybe 5 or 6 minutes. Okay, so just adding that hill in, because of some numerical issues as that thing steps down, just makes the whole thing longer. I guess Angelo was asking me what kinds of things I might use a server. I don't really know what its capabilities are yet, but and what I would use it for is to make not just these kinds of pictures, but really this kind of picture. And what this is instead of the loudness of the acoustics that we saw with the colors on the last slide at a single frequency, this is what's called a broadband calculation, where you do those calculations for many frequencies. We've got 10 to 30 hertz is what these are, and it's sampled every 1/8 of a frequency. So 160 of those single frequency computations, and then you do some signal processing magic to get these pulses. And these are really, I was really happy when these pictures came out before the conference. So these are really nice pictures. But this thing is for the flat ocean bottom. Again, if I started this in the morning, for the flat bottom case, it might be done by the end of the day, by 5 o'clock or 4 o'clock. Maybe not. But the more interesting ones, the downhill ones, I have to sort of start the day before, and they're not finished until the next day at some point. So my goals for some kind of server machine would be to speed up that kind of computation. Both from the sense of maybe we can refine the grid a little bit more, and also to we'd like to do these kinds of calculations not at 10 to 30 hertz, but at higher frequencies, maybe 75 hertz or so, where again you have to refine the grid more. Yes?
Professor, the Xeon that you're using today, do you happen to know the processor speed, gigahertz processor speed of it? Like
no, off the top
by
of my head.
chance? I'm just curious to see.
It's,
you had a few minutes. You had a few minutes to do this calculation.
It's
2.4 gigahertz.
I think it's the same as.
It's the same as
and
mass.
I think it might be 2.4.
2.4.
Quad core, dual quad core.
Dual quad cores, right. And I do this now with a sort of fake parallel processing. I'm using Linux. So I have a couple of directories with instances of this Fortran code in it, and so I can run them sort of side by side. But it's not; these are all Fortran codes, that we're messing with, and I run it on Linux because that's the easiest for me. But there's no inherent parallel processing. But yes, at 2.4 gigahertz, it's the
You say Linux?
Yeah, Linux. Yeah,
That's good.
I agree. So I guess I'm quick. Well, that's probably about it. Yes, absolutely.
Are there any particular libraries that you're actually calling from within your within your Fortran code, or is it just more straight Fortran?
It's fairly straightforward Fortran. There's no specific libraries. I know a couple of my colleagues do some different things with these codes and use LAPACK, the linear algebra package. But other than that, no, there isn't really any other specialized.
Pretty standard Fortran.
Yep, Fortran 77.
My question is more related to the implications of your study. Does it have any implication for like the United States Navy for submariners? Because my son's on a submarine, so I'm just curious.
Well, this is part of a grant that I got from the Office of Naval Research. So
really,
I mean they fund basic research where the implications aren't directly obvious, but that feeds into filters into things. So they're looking to find out about. The idea. I'll show you another couple of pictures here because we got time. The interesting parts of this work. So we've got, I mentioned the source in like an earthquake source. So here we've got this loud earthquake source, and the acoustics, the waves, which are shear waves and compressional waves in the bottom, but only compressional in the water, because water is fluid, it doesn't support shear waves. But anyway, the loudness, you can see sort of spreads out, and it's not very loud 10 kilometers away there in the ocean. The interesting thing is if you put in a downhill, which is a little hard to see on this picture, with the same kind of earthquake source, then all of a sudden you've got quite a bit more, 20 dB, which is, dB is a logarithmic scale, so that's, 2,000 times louder, just from this sort of shallow downhill thing. And this is the kind of mechanism that we think is causing some of those really deep compressional wave arrivals. So the Navy in particular is sort of interested in finding out how that bottom interaction works.
What are they hoping to gain out of this, Professor?
Well, again, I mean, they fund academic
top secret.
Yeah. Well, they fund academic institutions as what's called basic research, and so they fund a lot of things that they think they're interested in finding out about, but it might not filter into a genuine national security objective. So, I don't have a good answer for you.
Until next week.
Yes, exactly. In fact, I was warned by my grant officer at the meeting that they may be cutting everything by X%. So, we'll find out.
Would there be any consideration to converting Fortran to a more modern language that is suitable for parallelism and taking advantage of the
Yeah.
core architecture that is, out there right now?
That would be a great project.
Such as,
For instance, we're researching Scala right now and
Okay.
looking at parallel computations for computational finance.
No
And
languages scale.
It's a new, right, so a modern language called Scala, and it lends itself to parallel computing. In particular, I heard someone mention last week about MapReduce.
Okay.
It's a Google paradigm that we're actually using MapReduce. It's not Google's code, but we're using a pure Scala solution for MapReduce, and we're getting some amazing results.
All right. I mean, there's sort of a mixed answer to that question, which is, yeah, I mean, I in particular have a lot of trouble. I've spent a lot of years working in Fortran, but I still don't like it very much. I learned on C, and I would love it if there was a C version of these codes, but, you balance, you don't get any credit for rewriting code, So, that would be a great project for someone to do, but it's not in the works.
But there are libraries associated with Fortran that will, that will take advantage of parallel.
Yes,
especially
yes, there are,
anything
and that's another thing,
linear
it just
algebra.
hasn't really been, digging through this code to figure out where we could insert that kind of stuff. We want to get to this, but, and so that's how legacy things stick around. But,
The shape there in your source, the profile there, the jaggedy yellow,
Yeah.
is that a feature of the model or is that a refinement question?
no, that's a reflection off the layer here.
That's actually, that's not numerical, not computational, that's what it needs to be.
That's the energy's coming up and hitting this little flat portion here and coming right down. So these are the large angle propagations coming.
what is that hitting, Professor? What is it?
There's a layer here. It's hard to see on this slide, but let's go back to this one. There's a layer here of sort of sand and mud. And so that interface scatters the sound both down and up into the fluid layers. So that yellow is an acoustic. You see the same kind of thing here coming down.
Huh.
And that's a kilometer away. It doesn't look very far away, but that's a kilometer away.
Yeah, right. That's remarkable. It holds its shape like that. Because, huh.
Okay, do we have any other questions for Scott?